Okay, so we are going to talk about valence shell electron pair repulsion theory, VSEPR, also known as VSEPR, but even though it's not VSEPR, we call it VSEPR. Even yes, I know it's spelled wrong. The idea behind this is the geometry of molecules. Okay, or the shape of them. Okay. The shape of the molecules governs how they react with each other just as much as the atoms that are in them. And so I'm going to give you guys the basic shape. There's one basic shape. There's a simplest shape that all of the other shapes are kind of based on. And the idea behind it is valence shell electron pairs repel. Well, sure, but what do we mean by that? Let's start with a noble gas. So we're going to take neon here. What is the Lewis dot structure for a neon? Yeah, it's got its full octet, right? Okay, so these are the valence shell electrons, and we already draw them in pairs. Right? We've got this pair and that pair and that pair and that pair. When they start to bond with other atoms. Now, noble gases don't do that, but we're just going to do all 8 electrons to begin with. When these electrons start to bond with other atoms, these pairs become shared, right? They start sharing pairs of electrons. That was how we created our covalent bonds, right? Okay. These bonds will arrange themselves around a central atom in a way that moves the electron pairs furthest apart from each other. They repel each other. And it starts to look like this. And I'm just going to do it with the electrons for the neon. So here's our neon. And I'm going to do my best to draw this in 3D. Okay, ooh. And so on the top of a neon, we have this bubble, this orbital, this bonding orbital. You know what? Let's not do neon. Sorry. It's okay. Just place neon with a carbon. So we're gonna start with CH4. CH4. Here's carbon. And carbon's going to have a hydrogen, and hydrogen, and hydrogen, and hydrogen. This should make more sense. These electron pairs all want to push away from each other. They're not going to sit flat. They're not going to sit flat to just have a north, south, east, and west arrangement to the hydrogens. They just don't do that. Things that are allowed to move in 3 dimensions don't sit flat very often. Okay, they use all their dimensions. And so to get these guys away from each other as much as possible, our carbon has these 2 electrons out here bonding with a hydrogen. But then it's going to have another pair that comes out of the page to you guys, kind of like sticking their tongue out at you. And it's going to have 2 more that go backwards. back like that. So we've got one up here. So I'm going to try and visualize this for you guys. Oh, that webcam's not going to work. Okay, so we've got two of them coming out like this, right? And the other two going back like that. So these two are coming out like this, towards you, and these two are going back. You guys see that? Yep. Okay, another way to think of this is take fingers and go like this. Okay, and each finger represents one of those bonds. Yeah? Does this make sense to you guys? Okay. The shape that this makes our carbon here, the shape this makes puts a hydrogen on top. Okay, or it makes a tetrahedron. So if we draw lines between our hydrogens, we wind up with this tetrahedral shape. Does that make sense? Can you guys see that? The carbon's on the inside. Hydrogen, hydrogen, with the hydrogens at the vertices. This is the basic shape. This is called a tetrahedron. Okay, it makes this pyramid shape that has 4 equal sides to it because of the electron pairs pushing the atoms around. Okay. Okay. I don't want to go on to the next shapes unless we understand what's going on here. Does this make sense to you guys, what's happening? Okay. The electron pairs repel each other. They push each other apart as far as they can go, but still be attached to the central carbon. And the arrangement that makes is this tetrahedron. And our hydrogens are on all 4 sides. This creates this tetrahedral molecule.
So does it stay in that formation?
Yeah. Or... Yeah, so it stays in this formation. Now, this is the basic one. This is what they're all based on, this tetrahedral arrangement. But not all atoms are going to make 4 bonds. Nitrogen, for example, okay, can only make 3. Nitrogen looks like this, right? That's nitrogen. And so it's going to bond with hydrogens. But the electron pairs, the valence shell electron pairs, still repel each other. So this pair and that pair and that pair and that pair are all going to still repel each other in the same way that they did up here in the CH4. This is called methane, by the way. CH4 is methane. Okay, this is your most common association with this is what you release as a result of eating food. This is the gas, the primary gas that biological things release. Okay, there's CO2, H2O, oxygen, and methane. Okay. This is ammonia. This is going to look very similar. This is going to have our central nitrogen. And it has a lone pair. It's just a pair of electrons that takes up its own space. And then it's going to have these other hydrogen buddies. Okay, and this creates a similar tetrahedral shape. But the way we come up with our shapes is not based... they are made by the electrons, but the shape name comes from the position of the atoms. So, instead of a full tetrahedron, this one looks like a nitrogen with a hydrogen back there, and a hydrogen back there, and a hydrogen in front, and it's got this lone pair. And it's kind of a flattened. Yeah, that's not a good view of it. Sorry, what? Not a square. Well, I need you guys to see in 3 dimensions here. So maybe if I do my the lines you can see are solid, and that one back there is behind. As opposed to this up here. Okay, can you see how this one's kind of squished compared to that one? This is a full, all 4 sides are equal. This one is just like this one, except it goes to the middle, not all the way to the top. And this is called a trigonal pyramidal. Okay, not triagonal, trigonal pyramid. Okay, so it's a pyramid with a 3-sided base, but it's not the full tetrahedron like this over here. So we have tetrahedron, we have trigonal pyramidal. Okay, those are the more complicated ones. They get easier from here.
Wait, what's the difference?
This nitrogen has a lone pair of electrons sticking out of the top, but there's no atom up here. This carbon has a 4th hydrogen that's attached to that lone pair. Okay, it's this lone pair right here. Okay. All right, next one. Okay, y'all ready for this? Okay, is water. Okay, oxygen has how many electrons? Oxygen has 6 valence electrons. It needs 2 bonds. Good. Yeah? Okay. Well, based on what we just did, what is this going to look like? We've got oxygen in the middle. Okay. And it's got electrons. Oh, doing it the wrong direction. It's wide here, and it goes narrow out. And it's electrons sticking out the back, but then out the front, so we've got hydrogen sticking back to the right. We've got hydrogen sticking out in the front. And then we have these two just lone pairs, right? We have two lone pairs. Okay. The shape this makes, if you just look at the atoms, looks like that. Do you see how the hydrogens are not, they won't be in a straight line? No matter where they are, they're always going to be at this angle away from while they're attached to the oxygen. Yeah? Okay. This is a bent. This is a bent molecule. In fact, this angle right here is known. It is 109.5 degrees. This is a classic, we've known this for a very long time. Okay, you don't have to know the angle, but I do need you to know that it is not that. It's not straight across. It's not HOH and it's where it's 180 degrees. It doesn't work. You guys with me here?
Yes.
Last one. The example is going to be HCl. Well, it's second to last one. Sorry. It's the last one that fits this mold. HCl, well, Cl is green. How many electrons does chlorine have around it? Valence electrons. It's got 7. It's a halogen. And it's going to bind with 1 hydrogen. Well, there's only 2 atoms. If you have 2 points, what shape do you make?
A line.
Any 2 points. The only shape you can make with 2 points is a line. This is linear. Okay, and so you've got your chlorine here with electrons out the front, electrons out the back. And a single hydrogen next to it. And so the hydrogen and the chlorine, it just makes a line. It's just 2 points. It's a linear molecule, even though it's got these electrons sticking out the back over here. Okay? I'm going to give you guys the opportunity to make CO2. What do you think it's going to be? Okay, so here is our linear molecule. Here's our carbon dioxide. It's got 2 double bonds on either side of that carbon, and we've got the oxygen on either side. So that's going to create a linear molecule. Now, as we start making longer and longer molecules, or bigger and bigger molecules, each molecule has regions in it that have this shape. So that this group of atoms looks like this, but then it's connected to another group of atoms that's going to be bent, which is connected to another group of atoms, which is straight, which is connected to another group of atoms, which is kind of bent again. But it's all based on this idea in these shapes. Just like really big molecules. What really big molecules also have this idea that certain groups of them form patterns with their shapes, and those shapes stack and fold on top of each other to make bigger shapes. And it's the shape of the molecule that shows the function of it rather than the actual string of atoms. You guys remember this? You guys remember proteins from your biology? Okay. And how sometimes you have spirals in your protein, and sometimes you have flat sheets, and sometimes you have, sometimes you have like straight strands, and then all of those will fold into each other, and they'll create new shapes. Same idea here. In fact, it's these shapes that cause them to make their spirals or their flat sheets, or it's this VSEPR theory, this valence shell electron pair, is what allows our proteins to make these shapes. Okay, NH3 was going to be it's a much flatter pyramid, so it's trigonal pyramidal. This is tetrahedral over here. This is trigonal pyramidal. Then we had H2O or OH2, depending on if we're keeping our pattern here. This is going to be okay. Unfortunately, we don't call it triangular. Okay, we call it bent. And then we have our last one, which is pretty straightforward, like HCl. And this is no. Okay, and it's just linear. And we are also given CO2 is also linear. Okay. Those are the basic shapes. We will get more into these later at another lecture. Yeah, so that's our basic VSEPR theory.